Today, we are literally shrinking down to explore the bustling microscopic city of the revolutionary 8086 microprocessor. We're going to decode this dense piece of tech history together so we can build a crystal-clear understanding of exactly how modern computing architecture was born. It's a fascinating ride, so let's get into it.
Here is our roadmap for today. We'll start by meeting the microprocessor, comparing it to a microcontroller, and then diving right inside the 8086 architecture. After that, we'll look at the registers and flags, and wrap up by figuring out how this thing actually finds data using addressing modes.
All right, Section 1, meet the microprocessor, the brains of the operation. Let's lay the absolute groundwork here.
At its very core, you can think of a microprocessor as the electronic heartbeat of a computer. It's a central processing unit engineered onto a single microscopic integrated circuit chip. And what's wild is that it contains literally millions of incredibly tiny components. We're talking transistors, resistors, and diodes, all working together in perfect, absolute synchronization to do the computer's heavy lifting.
Now, the fundamental flow of computing is actually brilliantly simple. Input data enters from an input device, right? The microprocessor receives it, and then crunches that data using its internal components, the arithmetic logic unit, the control unit, and the register array, all while constantly communicating with a memory unit. Finally, it just spits the process results out to an output device. That flow is the heartbeat of all computing.
And you know, the sheer velocity of innovation during this era is just staggering. Take a look at this timeline. In 1971, we had the humble 4400 processor. It handled just 4 bits of data at a time with a tiny 1 kilobyte memory capability. Fast forward just a few years to 1978, and we meet our 16-bit hero, the 8086, making a massive, groundbreaking leap to 1 megabyte of memory. From there, the pathway goes straight to the massive 32-bit Pentiums of the 90s, boasting 4 gigabytes of memory. The evolution is just mind-blowing.
Moving right along to Section 2, processor versus microcontroller, heart of the PC versus heart of embedded.
So, we really need to clarify a common point of confusion here. What's the actual difference? Well, think of a microprocessor as the high-power, power-hungry central unit of a personal computer. It relies heavily on external memory and uses von Neumann architecture. A microcontroller, on the other hand, is a self-contained, low-power unit. It uses internal memory, Harvard architecture, and is specifically built for embedded systems. Think things like washing machines or MP3 players. Looking at the actual technical receipts here, you can see that because microprocessors need external memory and I/O components, their circuits are way larger, the overall system cost is higher, and their power consumption is, frankly, significant. They really don't have power-saving modes. Conversely, microcontrollers are incredibly compact. Everything is built internally, so they are highly efficient, utilizing idle and power-saving modes. That makes them absolutely perfect for battery-operated devices. It's all about choosing the right architecture for the exact job you need done.
Let's move into Section 3. Inside the 8086 architecture, the microscopic city. Time to zoom in and look at the blueprint itself.
The 8086 was an absolute historic leap forward, mainly because it featured a 20-bit address bus. Now, mathematically speaking, 2 to the power of 20 means it had the direct capability to address 1 full megabyte of memory. I know that sounds tiny to us today, but trust me, that 20-bit bus was a massive, industry-shifting architectural milestone for the era.
Looking at this diagram, you can see the architecture itself is logically partitioned into 2 distinct halves, the bus interface unit, or BIU, and the execution unit, or EU. These 2 units operate entirely independently, but they work together in absolute perfect harmony to get the job done.
Think of it like a functioning city. The bus interface unit is the city's transit system. It handles all the complex logistics, fetching raw instructions, reading data from memory and ports, and writing data back out. Meanwhile, the execution unit is the factory floor. It receives those raw program instructions and data from the BIU, and its arithmetic logic unit actually executes the commands, doing all the heavy mathematical lifting. Notice how the execution unit has absolutely no direct connection to the outside system buses. It relies entirely on the BIU to bring it materials.
And here is what really makes this entire architecture hum. Pipelining. It's totally genius. The BIU features an instruction queue. It's essentially a first-in, first-out group of registers where up to 6 bytes of instruction code are pre-fetched from memory ahead of time. By overlapping the fetching of instructions with the execution of instructions, the execution unit literally never has to stand around waiting for raw materials. This fundamentally and dramatically speeds up overall program execution.
So, where does the 8086 actually store all this data while it's actively crunching the numbers? That brings us to Section 4,
the registers and flags, the short-term warehouses.
The processor relies on 14 different 16-bit registers to hold things short-term. They're neatly organized by their specific function. So you have your 4 general-purpose registers, followed by your pointers and index registers, then your segment registers, and it's all rounded out by the instruction pointer and the flag register.
The factory workers on the execution unit floor rely heavily on those 4 general-purpose registers for their daily arithmetic and logic operations. Let's break them down real quick. You have AX, the accumulator, heavily used for input and output operations. BX is the base register, which is often used as a data pointer. CX is the count register, literally used as a counter for things like string manipulation and shifting. And finally, DX, the data register, commonly used to hold port numbers for I/O.
Now, with so much data flying around and complex math happening at literal lightning speed, you might be wondering, how does the execution unit keep track of its own system status? Like, how does it know if a calculation resulted in an error or if something went wrong?
The answer is actually incredibly elegant. It uses the flag register. It's a 16-bit register, but it actively uses 9 specific 1-bit flags. 6 of these are status or condition flags. So for example, it'll flip the overflow flag if a resulting number is just way too large to fit in its destination, or it'll flip the 0 flag if a calculation precisely equals 0. The other 3 are control flags, which dictate things like string manipulation direction or whether to allow system interrupts. It's basically a brilliant, highly efficient feedback loop.
For our final puzzle, we really need to understand exactly how the processor locates data in its vast memory space. Section 5, Finding Data, Addressing Modes.
Okay, the crucial point here is a fascinating mathematical trick. Remember a bit earlier when we established that the 8086 has a 20-bit address bus to access that 1 megabyte of memory? Well, we also just saw that all of its internal registers are only 16 bits wide. So how on earth do you create a 20-bit physical address when your registers can only hold 16 bits of information?
The bus interface unit solves this cleverly. It takes the 16-bit starting address from a segment register and shifts it left by 4 bits. Now, in binary, that essentially means just slapping 4 zeros at the end, which mathematically transforms it into a 20-bit base address. Then it simply adds an offset or effective address to that base. Base plus offset equals the exact 20-bit memory location. Think of it like this. It's literally like using a zip code and then adding a specific house number to get precise coordinates.
But how does the processor find that offset, that exact house number? It uses what are called addressing modes. The 8086 has a wide variety of these. It ranges from the implied mode, where there are no operands needed at all, to immediate mode, where the data is handed directly to the processor right inside the instruction itself. There's also direct mode, where the processor is given a specific constant offset memory coordinate to go look up.
And it goes way beyond the basics, too. The 8086 handles complex data structures with incredibly advanced addressing modes. Take the based indexed mode, for example. Here, the processor mathematically combines the contents of a base register, like BX, with an index register, like SI, plus a displacement value, all just to pinpoint the exact location of the data it needs. Whether it's scanning strings in memory or accessing an I/O port, these modes ensure the processor can navigate its entire memory space with absolute precision.
Looking back at this entire microscopic blueprint, one really has to pause and wonder, how did the elegant simplicity of the 8086's divided architecture, its clever pipeline, and its ingenious addressing modes completely pave the exact pathway for the multi-core gigahertz supercomputers currently sitting in our pockets right now? The foundational groundwork of literally everything digital we touch today was built right here, in this tiny 1 megabyte city. Thank you so much for joining